Good morning, everyone. Today, I'm honored to present our work, Task-Specific Gradient Adaptation for Few-Shot One-Class Classification. This research, conducted by Yunlong Li, Xiaobi Liu, Liyuan Pan, and Yuchen Ren from Beijing Institute of Technology, Few-Shot One-Class Classification, or FSOCC, is a task where only a few positive samples, also called normal samples, are available during adaptation, and the goal is to classify query samples as either positive or negative. This setup is critical in domains like anomaly detection or industrial monitoring, where only normal data is available during training and anomalies are rare or undefined. In the example shown on the slide, a task includes a two-shot support set consisting of positive samples only. The classifier or decision boundary must be constructed from the two positive samples, and then distinguish positive from negative data in the query set. A typical solution is OCMAML, which adapts the MAML framework to FSOCC. MAML aims to learn an initialization of model parameters theta that can quickly adapt to new tasks with a few gradient steps. It does this through a two-stage process: an inner loop for task-level adaptation and an outer loop for updating theta to improve performance across tasks. OCMAML extends this idea by performing adaptation on a one-class support set and evaluating the adapted model on a class-balanced query set. However, OCMAML uses cross-entropy loss during adaptation. It's inherently mismatched with the one-class nature of the support data, often leading to unstable gradients and suboptimal generalization. To verify this misalignment, we analyze the gradient dynamics. This figure shows three curves on the meta-validation set: loss variation along the gradient direction, gradient predictiveness, and effective beta smoothness, which reflects gradient continuity. OCMAML exhibits larger fluctuations and sharper changes, confirming that the gradients produced by cross-entropy loss on one-class data are unstable and not well aligned with FSOCC objectives. Another issue with OCMAML is its task-agnostic adaptation. It applies the same adaptation rule regardless of task-specific characteristics. This generic approach makes it hard to generalize well on diverse or novel tasks, especially in the one-class setting where support information is extremely limited. To address these challenges, we propose TSGA, an optimization-based meta-learning framework that introduces two key components: a loss network, which learns to generate smooth, informative gradients using feature representations and predictions from the one-class support set; an adapter network, which outputs task-specific hyperparameters, namely learning rate alpha and weight decay beta, allowing the adaptation process to adjust per task. Both modules operate during the inner loop. The outer loop still uses cross-entropy on the balanced query set to meta-learn generalizable parameters. We conducted ablation studies to understand each component's contribution. Compared to the OCMAML baseline, adding just the loss network improves gradient stability, adding only the adapter network improves task generalization, and combining both gives the largest performance gain. These results show that both components are essential and complementary for tackling FSOCC. More ablation results and architecture variations are discussed in the paper. We evaluated TSGA on OmniGlot, Mini-ImageNet, CIFAR-FS, and a real-world CNC milling machine dataset. In all cases, TSGA outperforms prior methods, including OCMAML and strong metric-based baselines like AHDD. For example, on Mini-ImageNet in the two-shot setting, TSGA improves over OCMAML by over 4% using the same conv4 backbone. Due to space limits, not all experiments are shown here. For more comparisons, please refer to the full paper. This slide visualizes the task-specific learning rates and regularization factors generated by our adapter network across inner loop steps and model layers. We observe that these hyperparameters vary dynamically across tasks, steps, and layers, highlighting the benefit of task-specific control. This confirms that the adapter learns meaningful meta-knowledge to guide adaptation beyond what static rules can offer. Thank you for listening. Our code and results are available on GitHub. I'm happy to take any questions.